All right. So as I said, today we cover some of the material that, first of all, the first part would be not going into the exam. Here, as I said, things are good to know. These things are good to know. You can write the programs that are aware of these issues. These would be inside the computer architecture material. Basically, it would go into, okay, let's think about if I have a program, how does it work? How does it actually transfer all these electrons and make sure that your computer, which kind of sit right here that I'm staring at right now, it works. It print correct output. How does this get processed, right? So one thing that we haven't really talked about for caching is we always think about lookup, right, as a read or write, right? You want to get some data from the main memory. But if you think about it, there's a difference between a read and a write. So what is a read? Basically, a read means that I want to look what is the value of my data. A write means that I have a value of the data. I want to save it, right? I want to save the data. So let's say I write something like this. AI equals BI, right? What am I reading from and what am I writing to? I'm reading from BI, right? I read the data of BI. I write that data into AI. There's a difference here. BI got read, and then I write that data into AI, right? So when you do this writes, the data actually changes. But if you think about it, how many of you here are running a computer that has multiple cores? So it's a multi-core processor, right? So anyone here are still using a single core processor? Guess no. I'm sure unless it's a laptop from 15 years ago, I think. Or even more, around like 20 years ago. Have you heard of Pentium 4? There was like Pentium 1, 2, 3, 4. Like when you were like still really like young, right? I guess you were even like less than 10 years old, probably. Like those Pentium 4, do you know what happened? Why do people come up with the dual core followed by this like core i3, i5, i7, which have multiple cores? Basically, in the architecture world, what we figure out is you have, I guess, Pentium, right? 1, 2, 3, and then 4. And it was like, hey, let's do 5. What happened is, if you look at the power that it consumes in terms of watts, these kind of go up like this. That is a log scale, which means that in theory, in reality, I think it's not a log scale, my bad. It's not really a log scale, but the power go up not linearly. It's actually y equal x to the 3/2, right? So that's not linear. So if you plot the power, it's going something like this. It's going up quickly, right? Which means that if you have, like, say, Pentium 6 or whatever, this single core processor, you might need a nuclear power plant to power it up, right? So people discovered, okay, instead of going toward this direction and make your clock as fast as possible, and you have like, I don't know, 20 gigahertz clock on your CPU, let's have multiple cores, right? So these are what you have is multi-core processor. So you have something like this. This is what you get when you buy an Intel processor or AMD, right? The same thing. You have core 1, core 2, core 3, and then core 4, right? So let's imagine this case, you are opening Chrome, right? What do you usually do on Google Chrome? Some sample load that you're running on Chrome. Let's say you're on Facebook, right? Browsing on Facebook. It's run on core 1. You might be running YouTube, right? On core 2. This thing maybe run something on that just render on Gmail, right? Chrome loves to have multiple threads. So this is what will happen on your computer when you have Chrome on. A lot of CPUs will be running multiple tasks from Chrome. So if you have YouTube and Gmail, you probably realize that they use the same account, right? You use your Gmail account to log into YouTube and also browse Gmail. And what does Google usually do? They store how you browse everything, right? This is actually the rage nowadays, which is like, okay, these companies know too much about me. What does it mean? Some of these processes share data. YouTube shares data with Gmail, maybe, right? Browsing on Facebook also shares some data because they're still using Chrome, right? So let's say I have cache, right? L1 cache is, let's just put it here, L1 cache, right? Right here. And then I have the share L2, right? And this data, cache block, right, is actually shared across core 1 and core 2. It's the same address. It's the same address. And then it just happened that whatever I do on Facebook, write into this cache block, writes new data into L1 cache. Can someone guess what can happen? So let's say this data is X, this data is X. This is a new data. We can say it X prime, right? Now you have 2 copies of X that are outdated. Yes, basically X get overwrites. Basically, it might be something like this: AI equal BI, right? This same code, right? So you have the old value of AI that get overwritten by the value of BI, right? So in this case, core 1, your Facebook program, right? Whatever Chrome tab that run Facebook see the new value, BI. The Chrome tab that run YouTube that might share the same data, they still see the old version of AI, the old value, right? So this is something you need to think about when you build a cache, right? Basically, if this happens, how can I make sure that this get updated to X prime and this somehow get updated to X prime. And then the cache block this same data in DRAM, right? It's also updated to X prime. So this is basically the process of handling writes, right? Any questions? Because this is actually not going to be on exam, I know some of you might phase out already, but if you want to learn about this, do you have questions? Basically, the key here is they share the same address. You just need to make sure that everyone see the same data when this data get updated, right? So the general policy is there are 2 policies. The first policy is called write through. When there is a write, you update the data everywhere. You update from X to X prime in L2, X prime in DRAM. Basically, once you update that data, you send a request to the higher level cache and the DRAM, the main memory, saying, hey, someone update this data, get this updated. Right? Another policy is write back. Basically, write back means that you are not going to update this data until someone evict cache block. That's okay too. If someone evict the cache block and then no one need to use that data in the meantime. you can update the data later. The additional policy involved, what if someone else need to read into that data? We're going to cover that in a computer architecture class. It's a little bit more involved, and it can be a little bit more confusing here because it has different policy. But right now, you just need to be aware that, hey, if I modify my data, I want to make sure that this new data is propagated into the main memory. Right? On the right, when you have a write miss, right? When you have a write miss, it's a cache miss, but it's a cache miss where you are writing something to that cache. You also have choices, right? Do we allocate? Basically, do we actually build a cache block for this writes when, right? So you can allocate when you figure out, okay, that's a cache miss. This is simpler. Basically, write would be treated the same as read. Every data access is treated the same. You can actually consolidate multiple writes to different level of cache. You can actually choose to like bypass. You don't do anything with the cache. Don't write this data in. If you figure, hey, you are not going to use it again, this is just one write to this one address and you don't need to read it afterward. Skip it. Okay, so these are different policies that the hardware designer can choose to improve performance. There's actually multiple things about cache designs, right? You can think about it this way. The last lecture we talked about the thrashing problem, right? Where you have the cache, and then you go to A, B, C, D, E, and when that happens, you never have the cache hit, right? So there are actually multiple works that people come up with that say, okay, we can have different policy that deal with these specific instances that kill the performance of the cache. There are different ways to make sure that data will not get mapped to the same set. You kind of spread it out, right? Spread it out the accesses so that it is evenly distributed so that you use every single space on your cache properly. You can deal with thrashing in different ways. You can even do something like in-memory compression and use that compressed data all the way through the cache. So there are actually works on different ones of these area that hopefully you get more when you buy this new processor. That's why when say iPhone update that processor, right? So how many of you realize that the clock speed of these processors, it doesn't go up by much every generation, right? But how many of you seen that plot? So how many of you listened to this like Apple iPhone release that conference, the one in September, where they'll introduce a new iPhone pretty much every year. How many of you listen to those kind of what's it called? That conference, the live version of that? Yes, no. So if you listen to that, yeah, not this iOS 14, the one in September when they introduce a new iPhone, right? In September, October, there's always going to be an event that they say, okay, this is our new flagship phone, iPhone 12, right? This September, October, there'll be another one that they introduce the iPhone 12, right? Last year, it was iPhone 11, before that, iPhone 10, right? And there'll be one guy who come in, he's like the hardware guy that say, okay, we introduce this new chip, right? That say this chip is the fastest ever mobile phone chip that is there in the world. And yes, that's true, right? That is true. And there'll be a plot that say, okay, that's how fast is that compared to the previous generation, right? And then if you look at the clock speed, and be like, how? The clock speed of the processor is not even that much higher, right? How come this chip is that fast? It actually have to do with a lot of architectural design, basically things like this, right? This cache design, it doesn't change your clock speed, but when you buy new processor, your cache is better. Your data is now more likely to be in a cache. Your main memory, the way you access memory is now faster, right? This is actually what architects do. We go in and optimize the heck of whatever hardware we have. Sometimes we just optimize on power. Your new phone would last longer. Sometimes you optimize performance. Your new phone would actually faster. Sometimes we just make a chip that is for different workload, like machine learning, right? So you can have this, play this Pokemon Go, right? And then you can use AR in there without burning too much of your battery. It's still pretty bad, but they're coming up with new chip to do this AR and VR workloads. So right now basically right now it's pretty much a rah-rah like kind of talk for why maybe architecture can be interesting for some of you, or knowing the hardware can be interesting when you want to develop a program. Another thing I want to let you know is with multi-core, even with a single core, data can be accessed in parallel. This won't matter on your exam because this is a little bit too in-depth. But think about it this way. When you have an assembly code, right? Assembly code, what's the requirement? You execute the first line, followed by the second line, followed by the third line, followed by the fourth line, right? That is also true in C and Python and Java, right? You do it line by line. Anyone disagree with that? You see the point, right? You finish the first line, followed by the second line, followed by the third line. If there's a loop, you go back to the first line again, then second line, third line. Agree? You all agree with that? All right. So this is actually what processors do. Let's say you have a code like this. Loop on AI equal BI plus CI. Right? So for A0, what data do you need? What is the piece of data that you need to compute A0? A0 is B0 plus C0, right? So you basically need to know what is B0 and what is C0. You need to know B0, and you need to figure out what is C0, right? How about A1? What data do you need to compute A1? From my code, A1 is B1 plus C1, right? So yeah, so you need B1 and C1. So from the program point of view, do I need to finish A1 before, do I need to finish A0 before A1 at all here? If ordering matter, does ordering matter here? Do I need to? Yeah, the answer is correct. Your answer is correct. No, you don't need that. Basically, I can try to find what is B0. I can try to find what is C0. I can find what's B1. I can find what is C1 at the same time, right? I can actually do this all at the same time. Anyone that want to stay with me on this topic, are you with me? Any questions? Or should I explain it again? It's yeah, it's true. Something like this is actually more like a graph algorithm. Basically, you figure out, okay, is my data ready? If my data ready, I can run it, right? So basically, in here, you can issue the load, issue the access to B0, B1, B2, B3, B4, B5. So does C. You can do issue the load to C0, C1, C2, C3, C4, C5. And modern day processor actually do this, right? This is called parallelism. Basically, you can issue this data access at the same time. Not exactly at the same time, but close enough, right? So you can do this in parallel. What limit how many data I can do in parallel? One thing is bandwidth, right? DRAM bandwidth can limit number of these parallel accesses. That's why sometimes your DRAM bandwidth can lower performance. Basically, when you write a program, even though you think that, hey, everything is parallel, everything is nice, I should get really good performance, run it, and then you feel bad because you did not get that performance that you expected. Sometimes it's because of the bandwidth. You don't have enough bandwidth to service all these requests, right? What does it mean? Maybe upgrade your DRAM, uh, or maybe figure out, did you use the cache properly or things like that, right? So knowing some of these things would allow you to identify when you need to debug your code or when you need to squeeze out performance, where in the code that you should look, right? It's basically go back to when you want to get performance, how you should modify the code to get that performance. Because you can't just randomly modify all the parts and expect that you're going to get performance. Hopefully, this allows you to do educated guess and minimize your effort, right? Another topic that you might come across in the future. This is called Belady optimal. Belady is a person's name. She wrote a paper on caching, and the paper is about ideally, this is the magic policy, and the key idea is that essentially you want to kick out the cache block that's going to be referenced the latest, right? That's it. That's the terminology. This is used as like an optimal baseline when you want to compare the performance of your cache or your program. When you write a program, someone might ask you, is this like Belady's optimal? Basically, is that magic point where you know exactly what will be needed later, and then you evict that block, right? And that's magical. You can't have it. It's just impossible. It's impossible to implement, but you can try to come up with a good like something that's close enough. And this is basically the ideal baseline where you want to test the effectiveness of your policy, the effectiveness of your program. All right, so that's it about replacement eviction. The other thing I want to talk about, we should kind of talk a little bit about this last time. It's called prefetching. Right. So most program, one thing I can say, this is predictable, right? If you have an array, most of the time you do for I equals 0, I less than n, I plus plus, and then you do ai equals something bi plus ci, right? That is super common. These consecutive accesses throughout your array is really common. Agree? Or disagree? Anyone disagree with that statement? So do you agree that when you use the data, there are trends? There are trends that you can predict. What is the next piece of data I will access? If I access A0, I might be accessing A1, right? That makes sense. This makes logical sense, right? When you go in a loop, you look at how much you increment I for every cycle, and you predict what I'm going to access next. So this means we can guess. We can guess what data a program might need, which means that I can build a cache that can learn patterns, right? I can learn the pattern and I guess it ahead of time. And these things exist on your Intel processor and AMD processor. There's these thing called prefetch instruction. You can actually put that in the assembly code this line, prefetch n mean the level of the cache. So prefetch 1 means that bring whatever this address into the cache, into the L1 cache. Prefetch 2 M8 will mean that bring the address M8 into the L2 cache. Because as a software programmer, you know that whatever address M8 is, I'm going to need it in the next few instructions. Are you with me? Basically, you can insert this instruction that say, I know I need that data, so I'm gonna tell the processor, bring it in ahead of time. Bring it in ahead of time so that I can avoid the cache miss, right? And there are multiple things you can do. So this is a software guided. Basically, you as a programmer would write this code, right? The hardware can do it automatically as well if it's super easy to predict. For example, these thing we call stream is if you have something like this. First, you access A0, followed by A1, followed by A2, right? Followed by A3, followed by A4. If you see this, what is your next access? Anyone want to make a guess? What is my next access? Yeah, it's really high chance that the next block you're gonna get is A5, right? Followed by A6. Dot, 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 right? And how common is this pattern? Like how common is this? It's everywhere. If you look back at your code, if you look back at your code in Java, in Python, in C, you see that this happens all the time, right? Anyone disagree with that statement? I write the code this way all the time. Yes, no? Agree? Yeah. So at least one of you agree with me, saying, "Hey, I write the code this way all the time." So if I need to decide, like, build the cache, what do? I can build a cache that observe that if I'm doing this and say I'm here, the next thing I'm gonna do, I'm gonna grab the next cache block, bring them into cache. Make sense, right? Does it make sense to you? Basically, if I see this trend, I'm gonna grab whatever is coming next into the cache. And this is actually possible. It is actually one of the areas that people actively are working on. What would be the best thing we can do here, given multiple different access pattern? Another pattern is called stride, right? Something like this. How often is this? You go to A0, followed by A4, followed by A8, right? Followed by A12, right? What's next? What will I access next? A16, followed by probably A20, right? So how about this? What if I do A0, A1, A2, A4, A8, right? A16, A32, right? Both of these has pattern, right? Based on the index. Index just gets updated in a certain pattern, and this happened a lot as well. So you can actually build the policy to get this data ahead of time as well. So now we basically can prefetch cache block in strides, right? So these are different things you can do to the caching policy to actually get more cache hits, right? what I covered earlier, if you want more performance, there are a few things you can do. Issue fewer loads, right? You change the program to issue fewer loads. You can change the cache to make it faster. You can do this. Prefetch to get more cache hits, right? You can do that in a software using the prefetch instruction. You can do that in the hardware by changing the cache. You can make DRAM faster. So these are a few things that can significantly improve performance. All right, that's it for the new material that will not go into the exam. We will come back to our class. Now we're back to system skill. Recap, right? Recap. Come back here. If you phase out, come back here. This is a recap of the last two lectures. I want to make sure that you get at least, first of all, the high level overview, right? I give you this example. Let's say I want to buy milk or coffee beans. The first thing registers the quickest place you can go to, your fridge, your pantry, your home, right? Then if the thing you look for is not there, you need to, I guess, walk to the nearby 7-Eleven or nearby market, right? To actually get what you want to buy. That's the cache. If the cache is the nearby market or 7-Eleven doesn't have the item that you're looking for, then you need to go to a bigger outlet, like a mall, Big C, Lotus, or Central, or whatever is closer, right, around your area. That's your main memory. If they don't have it, you kind of cry in the corner and say, okay, if I really need it, I probably need to get it at the source. That's the disk, right? Or if the disk on your local machine, on your desktop doesn't have it, what do? Maybe it's on Google Drive, right? That's even slower. So that's kind of like you need to fly away from Thailand to get whatever you want. That's the high level overview of this hierarchy, the memory hierarchy structure. Here's the organization, right? Cache consists of multiple cache block. It has multiple cache block. Each block will be mapped to a specific set. There's a one-to-one mapping. Each block go to only one set, something like this. There can be more than one blocks per set. So from this example, how many ways am I looking at? Is it direct map cache, 2 ways, 3 ways, 4 ways, 5 ways, 6 ways, 7 ways? Can someone tell me how many ways am I looking at for this particular cache? Yes, 2 ways, right? Because each set contains 2 blocks. That's 2-way set associative cache. The process of looking up is essentially to check if I have my data in the cache or not. Right? An address is divided into multiple bits. The first important piece of information is the index bits. This tells me what set am I going to. The next piece of information is the tag bits, which tell me, okay, I know it's going to that set. Here is the ID of my cache block that I'm looking at so that I can check if the data is there or not. So how do you get both the index and the tag bits, right? So you look at the cache block. The least significant bits are for number of accessible location in your address. So it's log of that inside the cache block. Then you compute log 2 of the number of sets. You get that number, let's say it's M. That M is the set bits, the index bits. The rest are tag bits. So these are the formula. If you're confused, come back to this formula. If you're still confused, come back to office hour. I'm gonna explain it again in the office hour if you're confused, but I think I did it like 4 to 5 times already. So hopefully, if you listen to 1 or 2 of those times I'm explaining, you kind of get the high level idea. When you do the in-class exercise 9 and 10, you can check with me if you get the answer correctly or not, because I can assure you the exam would have something like that. I can't be more obvious than this. There'll be exam questions that ask something similar. Are you with me? Basically, make sure you can do that before the final. All right? Set associativity is basically its number of cache block in a set, as I said earlier. This is a specific term that we call set associative cache. N-way set associative cache means that there are n blocks per set. One of the policy that we assume for this class is the LRU policy. This is based on two things, temporal and spatial locality. So if I ask you what's temporal locality and what's spatial locality and give me some example, hopefully you can give me some example. All right. Why does this make sense? Why does the LRU policy make sense? Can someone take a stab typing in on the chat to say why LRU would be a good policy? Because of that reason, exactly, right? Essentially, this is just how you write your program. Your brain typically just use whatever you just declare, whatever you just put in, right? So at the end of the day, the LRU would exploit how human use data, how the algorithm that human design use the data. Can something go wrong? Can I get 0% hit rate from the LRU policy? The answer is essentially yes, right? Thrashing, yep, exactly. Basically, you have set thrashing, something like this. If you have A, B, C, D, only 4 ways, and you loop on A, B, C, D, E, because I explained already from the last lecture, I'm not going to go through them again. But these make LRU ineffective. How bad? A random policy is even better, right? If you pick random block to kick out, you're going to get some hit rate. You're gonna have some cache hits, right? It is going to be strictly better than the LRU policy. All right. There are 3 types of cache miss. Compulsory miss is when you see the cache for the first time, you can prefetch to get rid of this type miss. You can have conflict miss where you have thrashing. Thrashing leads to conflict miss. Capacity miss is when you don't have enough money to buy big cache. So basically you cannot cache everything. When the workload is too big, you need to go to main memory. All right, that's all for recap on caching. I'm gonna give some preview on virtual memory, but before we move on to virtual memory, any questions about caching that you want to ask right now? Okay, enough time for typing in question. I assume that no one is typing in anything. There's no questions. So please go through in class exercise 9 and 10. We'll have time to do it today around maybe 3:15. I'll actually give you some example on how to actually go through in class exercise 10. Right now, let me give a brief overview of what's coming next week. Next week, we'll talk about virtual memory. And this is what you want from the programmer, right? You see the abstract version of main memory. when you call malloc, what do you get? You get some address, right? And hopefully you feel like, okay, I have unlimited memory. The memory is contiguous. You don't have to think too much about where they are. You know it's an address. You don't have to think about what will happen. What will happen if I have two programs running at the same time? Program A and program B. Right? And this is your DRAM. Let's say I have program A owns this, program B owns this. When you call malloc, do you need to worry about where is your data? As in like, do I get it from here? Or do I get it from here? Or do I get it from here? Do you ever have to worry about that? No, yeah, these are all being abstract out, right? This mapping is managed by virtual memory. And we will learn, so in the next lecture and going forward, we will learn what happens here. How can you make this benefit? How can you provide this benefit through virtual memory? A really quick how is the operating system and hardware work together to give you this illusion. And inside the hardware, be aware that this is a physical DRAM. So somehow, once you hit DRAM, your virtual memory, your virtual address would have to become physical address. So there has to be something going on inside. And here are the three main benefits, right? The first benefit is, as we saw earlier, you can have DRAM down here. And this is what your program sees. I have data here for array A. You have this data here for array B. You have this for array C. Okay? And somehow, these array A, B, and C would be mapped and managed by the virtual memory. You don't know where they are. It will magically be accessible, right? This way, what are the benefits? This way, you don't have to worry about, okay, what about the other program? Are they running? Are they gonna come into my address and somehow mess everything up? You don't have to worry about that, right? So you see the first benefit clearly over here. This is our abstract away. You have this virtual space that you can manage as long as you call malloc correctly. As long as you call malloc correctly. How you use the data inside the block that you malloc, it's up to you. You can do whatever you want with it, right? So that's the first benefit. The second benefit is this. You have program A and B, right? Program A and program B. So let's say this is Microsoft Word and this is Chrome, right? This is owned by A, this is owned by B, this is owned by Dota, right? What you have here is you probably want to make sure Microsoft Word can't look into what are you doing right now in Dota, right? What you're running on Chrome, so should not be possible. The only legal access should be to whatever you own. The same thing goes for program B. You can be able to access whatever you malloc, but you should not be able to look into what am I doing in the Microsoft Word unless you give them the permission, right? Same thing here. Any questions about memory protection? Basically, it protects you from looking into someone else's program. And I can assure you, every one of you here right now are taking advantage of that on assignment 2? Can you give me the example of that? All right, let me rephrase my question. Basically, these protection, basically what it does is it prevents illegal accesses, right? It makes sure that if I run this program, this new program cannot modify the content of another program. It protects illegal accesses. It protects illegal modification to my data from another program. So from assignment two, how many of you got sick of segmentation fault? Yes. All right. Everyone here is so sick of segmentation fault. Let me tell you what happened if you do not have segmentation fault. When you have segmentation fault, what is happening is you're basically trying to access some data that you did not own, right? Most of the time, okay, that's a good question. So let me put it this way. When you use a variable, so the question is, I don't understand why we have to use pointers. Why can't we just use variable? The answer is yes, you can use variables for sure. When you declare a variable, it's the same as you declare a pointer followed by malloc. And then when you exit that function, you free. Right? That's what variable means. You declare that pointer, you malloc area for that pointer, and when you are done with that function, you're free. Are you with me on that, at least for that statement? If you use variable, say int I, right? Int I means that you're gonna make space for I, and then when you finish whatever we do with that function, you free that space. Yes, no, are you with me? Okay. The problem, I guess the limitation of using variable is, so what if I want to return 5 pieces of data? Or if I want to return an array, can you do that with variable, or can you not do it with variable? Yeah, so basically, if you want to do that, you need to use a pointer, allocate the data. Yes, you need to do it through pointer. In Java and in Python, it's kind of the same, but the engine, the Java and Python runtime engine, they do that for you. Right? Basically, they do it for you in Java and Python. In C, it's super bare bone that they are not doing that for you. So you need to do it manually. If you move from C to C++, if you move from C to C++, some of them is a little bit more convenient, actually, because you have the object-oriented part of Java. So I know you're sick of pointer. I totally understand. Once you move to C++, things would be better. So when you actually go on a job and you know how to program in C, I'm sure you will know how to program in C++. It's just C with object-oriented. The reason we need to use pointer is if you need more than one piece of data when you want to return or when you want to call a function, you can use a pointer, right? And then, okay, let me go back to my original question that I'm asking you. How many of you got sick of segmentation fault? And I can guarantee you right now, everyone's sick of it, including myself, right? I can tell you how many times I've seen that when I program on my own, right? It's normal. Okay, so let me follow up that question a little bit. So the question is, well, you understand that you have to allocate some memory, but do you have to do it using a pointer? Yeah, yes, for C, you need to use pointer for that. It is like it's the correct way to do things in C language. I'm not going to say is that the best way to do things or not. This is up for discussion, right? There are certain benefits you can get from C, and there are certain disadvantages that you probably realize, right? It's not easy to program. It's easy to make bugs. Sec fault kill you and me. Uh, so yeah, what happened when sec fault? Can someone guess what happened when you have sec fault? So if I have program B that I want to access this location, you go through virtual memory, you go to virtual address. What you get is the OS. The OS would tell you, hey, that you did not own that. You did not own that. So they tell you seg fault. Basically, they'll tell you this segment of memory is not, it doesn't belong to you. This segment of memory doesn't belong to you. Segmentation fault. That that's a historical reason behind the word segment. It's how Intel implement their virtual memory. But the idea is you're trying to access some location that you did not own. So the OS will protect, right? It will protect that location from this buggy program. Because when you have seg fault, you have to also admit that your program has bugs, right? Everyone is agree on that, right? You have bugs, otherwise there will be no seg fault. This bug specifically is illegal accesses, right? So that's what seg fault means. And it's a good thing actually, because let's say you are trying to modify some location and you have a bug, it causes seg fault. Without that seg fault, let's say that address owned by Windows. Can you guess what might happen? Guess what might happen without the seg fault? Yes, the whole thing can crash. Basically, if you forgot to save your program, now your program is gone because the window just, okay, something's wrong, I'm gonna reboot. Bye. Right? That's it. That's why protection is important. That's why it tell you seg fault, because Windows is telling you, hey, don't run this part. If something is wrong with this, you go and debug it, but it's not safe. All right. So the last part is we're not gonna cover about this right now. We will do it next lecture. But the third benefit is, let's say you buy a DRAM, right? How big is your memory? Can I ask some question related to your machine? Can someone tell me how big is your memory right now? 8 gigabytes, 16 gigabytes? Pick me some number. Tell me some number. All right, let's say you have 16 gigabytes. How many of you are running with 20 different Chrome tabs at the same time? Admit it. Privately is fine. I'm sure that at least one of you who occasionally have 20 Chrome tabs. Awesome. Me too. I do it all the time. So let's say you have 20 Chrome tabs. Let's say you open the task manager on Windows. Okay. What you see here is you see Chrome, 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 Chrome. Have you seen this? Okay, yes. When you're searching for the solution for your bug. Yeah, I totally understand that. So you see a bunch of Chrome on the task manager, right? These are different processes. If you go back to our Linux lecture, when they talk about thread versus processes versus program, I use the same example. Let's say this use 1 GB. This use 1 GB. This use 2 GB. This use 1 GB. And let's just say at the same time, you got sick of debugging, you want to take some break, right? So you go play Dota. How much memory does it consume? I actually kind of forgot. I used to play a lot back in the days. Let's say it's like 5 GB. So how much memory in total am I using right now? So it's 5 plus 2 plus 2 plus 1 plus 1, right? So that's 11 already. This is okay, right? You have a lot of memory. What if I have more processes, right? This one use 4 GB. This one use another 4 GB. Is this more than 16? Yeah, so this is actually now more than 16 GB, right? Does your window crash? So my question is, does your window actually crash? So actually I'm asking you two questions. Does it crash? The second question is it slower? Is it a yes for crashing? Does it crash? Yep, it's going to be slow, but it will be there. It won't crash, right? So this is what virtual memory give you. Some of these data. So right now, how big is it? 18 plus 11. So this is 19 GB, right? What happened is, out of this 19, the 3 GB, this go to your hard drive. It actually get kicked out of your memory. That's why it's slow, because somehow if you need to access it, you need to go to the hard drive. That's the reason why they are slow. The reason why they are not crashing at the same time is you can actually put, using virtual memory, you can actually kick something out to the hard drive. So it will not crash. With the SSD, it's faster. I would just say it's faster. It's not that much better. What you want to do is to make sure it's still under the limit. What you want to make sure is, at least if this happen all the time, maybe just buy more RAM. Uh, but it won't crash. With the solid state drive, it's better. It's better than a hard drive for sure. Uh, that's why if you have a machine with the SSD, this is one of the small fraction of reasons why your computer is faster, but it's not every reason. There are actually many other reasons relate to how you use the disk that SSD provide better performance. It's mostly about how you access the file. It's not about the virtual memory. It's a different system. It's a different part of the OS. But the fact that it doesn't crash is the benefit of a virtual memory. The fact that it doesn't slow to a crawl is also the benefit of the virtual memory, because it actually pick what go into the hard drive and it pick what stays in DRAM. Anyone want to guess the policy? Anyone want to guess the policy on how the OS would pick what goes into DRAM and what goes into the cache? I mean, not cache. Okay, I'm just hinting you that. What goes into DRAM and what goes into hard drive when you need to use more than what you have on DRAM? What policy can I use? What is one policy that I told you already in the caching lecture? What can be my eviction policy? Oh, so quiet right now. So you can use something like, yes, yeah, okay, thank you. Yeah, it's something in LRU. It's actually imitate LRU. Basically, it's a cheaper version of LRU. That's why it's slow, but it's not way too slow. Okay, so that's it. That's it for the virtual memory. A quick high-level overview of virtual memory is, let's say you have multiple programs, right? These are the data in the program. Program A, program B, program C. You have DRAM, that's one piece of physical memory. You have this virtual world. This is the physical world. There is some mapping between these data that manage where things are. You have the mapping between the virtual and the physical world. That's a high level overview. So next week we'll learn how this is done. We'll learn how this process is done on the CPU, on your processor. If you're curious about anything beyond this, let me know in the office hours, because actually, I think I'm the second person who kind of proposed this idea on GPU in the world. So I'm pretty sure I'm the second person. So if you want to look into like how virtual memory works beyond the scope of the CPU, let me know. I'm that person in the world to talk to. Okay, so that's it for the virtual memory preview. Next week we'll learn how to do this, how this is done. Before we leave today, I've actually prepared another set of in-class exercise for you. Please finish exercise 9. We already covered exercise 9 to some extent. So what we'll do today, right now, given that we have about 45 minutes left, don't leave yet. I'm gonna kind of walk you through some of what I have on in class exercise 10. First of all, please open it on Canvas. I'm gonna do the same here. All right, and I'm gonna create a few more collab edit documents, just 3 of them, so you can use it as a scratch pad. We will do this in group again. This is the first link. So pick one of these links. It's on the chat right now. I'm gonna put you 3 links here. So you have a shared worksheet that you can take a look at.